Good morning, everyone, and welcome to this webinar on CFD applied in architecture. My name is Alessandro Palmas. I'm one of the co-founders and developers at Conself. And today, I'm going to show you how to apply these innovative and powerful instruments, CFD, on typical simulation that may be found in the architecture and buildings sector. First of all, a few words about Conself. Our mission is to help innovative small, medium enterprises and freelancers improve the engineering design of their products. And how we are going to do that? Providing design software easy to use and accessible everywhere. Our core business is the CFD on cloud. We provide a state-of-the-art CFD software directly in your browsers. Together with it, we also offer other services as consulting with dedicated development and tailored activities and product optimization, support with qualified technical personnel, events like these webinars, and training, both on-site and remote served. Let's now focus a little bit more on the CFD on cloud service, and I'm going to show you few features about our product. Then later on we are going to apply it on a real application in the architecture field. So first of all, the advantages of having a CFD on cloud. First thing, you can forget about license. Since you're going to pay just for the simulation you need, allowed by the software as a service approach, you don't need to buy expensive license anymore. Relying on cloud computing, you don't have to buy high performance hardware. And with our vertical application and automated workflow, the know-how barrier, there is, something really not more as crucial as it was before, since the majority of settings will be really straightforward. Finally, the budgeting is not needed anymore, since you can pay just for the simulation you need for a specific case. You can charge them on the customer. This means saving up to 90% if compared with the most standalone softwares. Someone may ask, why cannot rely just on experiment, on physical experiment instead of simulation? Well, there are a lot of reasons why simulation can really make the difference with respect to experiments. Let's say the number of parameters you can analyze with simulation is basically limited, and the space and time resolution allowed by simulation cannot be compared with experiments. In addition, the test scale, as well as the types of studies you can realize with experiments, are very limited if compared with the real scale simulation and hazards and dangerous scenario you can simulate with CFD. So let's see how the CFD simulation is carried out with our software. There are 4 steps. The first one is the geometry, where you create and upload your CAD model. Then there is the definition of the geometrical grid. It means subdividing your fluid domain in small parts. Then the definition of the CFD setup with both model choice and boundary condition, and finally results analysis. Let's dig a little bit more in each of the steps. The first one is the geometry. You can upload file of different formats, as you can see, from STEP, IGES, and STL, and different Unity system like International One and Imperial. There is the possibility to automatically create a wind tunnel for external flows. About grid, we can provide you two different meshing algorithms, like hexahedral and tetrahedral one. In addition, we provide also a boundary layer for wall refinement and a guided procedure. Since we divide the meshing into different steps, the first one is the surface meshing and then a straightforward volume meshing. About CFD, you can simulate both incompressible and compressible flow, both laminar and in-viscid, as well as turbulent flow with the K epsilon, K omega, and Spallard-Talmaras models. And finally, the simulation can be both steady and unsteady simulation. We want to stress here that we rely on OpenFOAM, that is a well-known software. It is validated, and its accuracy is confirmed from a great number of works developed from many universities around the globe. About the result step, we rely on ParaView, a well-known post-processor scientific data handling tool in its web-based form. That is web. You can use ParaView directly inside your browser, and so you can extract slices, streamlines, profile, contour. We are going to show you how to do that on our web-based application. Even more, apart from these features, we can provide you support that, available directly online, and test cases and tutorials, you can find them on wiki.conself.com. The hardware is available 24/7 with potentially unlimited CPU power. And finally, we can provide also dedicated software development in case you need specific application for your sector. So let's now dip in our case study today is a very simple building geometry in a wind tunnel, in a fluid domain, and we're going to see how the wind entering the domain interacts with the building. It's a very simple one. This, in order to be as clear as possible in all the steps of the simulation and also to save time. But I want to stress that if the same approach is applied on a very complex suburban or urban area, the result will be exactly the same. Of course, it may need a higher number of elaboration, and maybe it may take a little bit more time to implement every steps and also to complete the simulation, but the steps are they're really same. So first of all, what's our objective? Our goal today is to study the airflow in a urban area, and then to analyze pedestrian comfort. It means the highest velocity on ground and how they are distributed, and the structural loads on buildings. This is our geometry. Is a clip of the fluid domain that is symmetrical, so you can reconstruct it by just mirroring it. And as you can see, it's a colored geometry. In fact, this is the best approach in order to exploit every feature of our software. The best thing to do is to upload a step file with colored boundaries. This way, you can define different surfaces that will be automatically recognized inside the software. And this is useful for two reasons. The first one is to assign different meshing refinement on your body. So this is the mesh part. And on the CFD side, the different coloring allows you to define different boundary conditions for your modelization, your fluid modelization. Let's say In this geometry, from the CFD point of view, there are basically three different types of surfaces. That is the inlet, the red one, where the air enters the domain, the outlet, that is the gray one, but also the ceiling and the lateral walls where the air flows out, and the walls that are basically the ground, this white, and the building, and also the yellow here. So why we used many different colors? It's not because we need it for the CFD, but we need it for the mesh. In fact, everywhere you see a different color, you can say a different mesh refinement. It means that here, that we are near, very far from the building, you can say a coarse mesh, saving cells. At the same time, on the building, you can apply a very fine mesh in order to improve accuracy. So these are main reasons to have a colored geometry. Now, let's start recognizing each part of the geometry. The red one is the inlet where air enters. We are going to apply a uniform wind profile on this one of 2 meters per second. The outlet where the air flows out is here on the gray part, and also on lateral walls and on the ceiling. The ground, as well as the building, are walls where the air is lowered down to 0. In fact, you can understand that from it's something that it's natural, where the air touches the building and also the ground, it slows down up to 0 because of friction, okay, and other condition. Now, after these premises, let's see how practically we can perform this simulation on our web application. So let's just switch to a common browser. Okay. So here we can start from the home page of Conself, conself.com. In order to log into the web application, you can just click here on the top right bottom, and you will be redirected to the My Account page. If you already have credentials, just log in, or otherwise you can register here. I'm going to add my credential now with user and then password. So this way, we will be inside the web application. And there are two tabs, dashboard and simulation. The first one presents you a few information about your account. The most important one is this, where it presents you remaining credits and use it once. As you can see here, you can have a direct link to the manual or to contact support. Now we want to start the simulation, so let's go to simulation and create a new case. Let's call it building. And just click in create. We are directed to the simulation workflow, where you can see there are those 4 steps. In fact, geometry, mesh, CFD and results. Mesh, as I told you, is divided in surface mesh and volume mesh. So the first thing to do is to upload your file that you have on your PC, and that's it. Then you have to choose the units, in this case millimeters, and then the grouping criteria. As I told you, this is the colored step file. The best thing to do is to group surfaces by curve color. Clicking next. You have to choose the domain. In fact, is it an internal flow or an external one? In case of external flow, you are required to insert the bounding box. It is useful, for example, when you have to simulate external flow on a vehicle. Let's say you have to put the vehicle inside a wind tunnel, and the bounding box is the wind tunnel itself. In our case, our building is already inside a bounding box, so it will be an internal flow. Clicking submit, the system starts, and as you can see, the geometry steps are reported in the window case in progress in the simulation tab. This progress bar here shows you which percentage of the process is completed, and once it reaches 100%, you can find your case in the selection here. And we are gonna proceed with the case I have already in my account, even though, as you can see, the geometry step has already finished, but we are gonna continue with our webinar building that is the very same geometry. So now we are in the Mesh 2D step. We just run geometry and we have to load it here, starting from step and inserting here the previous step. This way, it loads the file here, and as you can see, we have our file. We can see we have here a list of boundaries grouped by color. We can see each of them highlighting the name. Here, for example, the building is magenta, so we can just select it, click OK, and here is it. Here it is. This is our building. So now, for each boundary, we have to assign a refinement level, a refinement measure, mesh size for the surface meshing. So there are mesh coarsening and mesh size. For this case, you can assign to all boundaries 0.04, except to dark orange, where you have to put 0.01, white, that also has 0.005, and magenta with 0.0052. When you complete the whole list, you can just click submit, and for the preview steps, you will see the case in progress in the simulation tab. And let's skip this part in order to speed up the process and just go to Mesh 3D. When your Mesh 2D is completed, you can find the result here. And as you will see, there is the very same geometry, but there is an important difference. In fact, if highlighting the file, I choose the representation surface with edges, it will show us the mesh of our body. And as you can see here, there is a higher refinement in the region near the building with respect to the region far. This is the reason why we selected two different colors for our geometry in order to define two different mesh refinements. As you can see, this is the white part with the different refinement than the orange one, and also the building. Now, you can just select your meshing algorithm for the 3D, for the volume mesh, and the max element size. That is the max element you will find inside your domain. By clicking next, you are redirected to the boundary treatment. In order to understand how it works, just open the user manual. You can find here all information about how to complete the simulation with our web-based application. And as you can see here, there is the difference between the hexagonal and tetrahedral mesh, as well as the explanation on how boundary layer works. But now, for our case, we don't need boundary layer, so just leave the default values with layer number 0, and that's it. So then click submit, and you will have your volume mesh completed, so we can proceed to the CFD part. At this point, again, we have to choose the step from where to start. That is the mesh 3D, the last one we run. And we will see that again our geometry here, but with a major difference. In fact, in this case, if I perform a slice of our geometry using the plus here, sorry, you have to highlight the file and then to the plus slice, you can just click surface representation with edges, click OK, and then as you can see, inside the domain we have the cells. So the volume mesh have been performed, and we have the fluid domain subdivided in smaller elements. Now let's focus on the CFD part. First of all, we have to choose the density model. It means is it a compressible or incompressible simulation? For this one, we choose incompressible since velocity are quite low. The fluid viscosity we want to perform as a turbulent analysis, so Spalater-Maras model works for us. Then define density, and that's it. We the air density, dynamic viscosity again, and then the initialization of these variables. Pressure initialized as the pressure, we need 1 atmosphere. Then the velocity, let's say 1 meter per second as initialization, and the Spalater-Maras variable. Sorry. We can now focus on boundary conditions. So we basically have the walls where the velocity will be 0, and they are the dark orange that is the ground. And for this part, as well as all other walls, the default values are okay. In fact, you have a 0 gradient, a 0 velocity value, and a 0 gradient for the turbulence variable. So dark orange as well as white and magenta are okay with that. So let's now define the red, that is the inlet. We have a 0 gradient boundary condition for the pressure. We have a uniform velocity along the x-axis. As we said before, we're going to use 2 meters per second, and a value imposed on the boundary on the value of the turbulence variable that you can evaluate again through the manual. Here you have the reference table to evaluate how much to put in that field. So that's it for the inlet. Finally, we have the outlet. I'm gonna choose the gray that is in the back part of your domain, and we can assign a value of the pressure, that is the atmosphere value, and then we're going to assign a gradient 0 for all variable gradients, as well as on the turbulence variable, and you have to apply this also on other lateral walls and the ceiling. So that's it. We can click next. And finally, the last thing to do is to choose the time evolution. We can have a transient or unsteady, or a steady simulation. In this case, it's steady, so you have to prescribe the number of iterations you need and the output frequency, how many times you want the system to save your simulation results. And again, you click submit and the process starts. We are going to skip that, and we will go right straight to the results. Here you can upload the results of your simulation, and we will have the geometry we already know here, but now we have also variables on it. So first thing to do is to click on this small clock and then go to the last iteration. It means the very last value evaluated on our domain. And now we can start to analyze the results. Let's start with the slice where we want to plot the pressure contour, how it evolves from the inlet to the outlet passing through our building. So let's now choose our file and choose the slice. Here we want to have a slice with the normal oriented as Y, then we can just click apply. And then we want to limit the minimum value on 1, 1, 3 to 4, just clicking apply. You will see here how the pressure is distributed along this slice. As you can see, moving from the inlet to the outlet, the peak of the pressure is encountered at where the airflow it's on the building. And in fact, here you have the peak of your pressure. Then it falls down on the back part of our building. This is something, I mean, very simple to understand, but it gives you a quantitative way of measuring it. And in a complex geometry, interaction between buildings and flow may be not so straightforward. But now let's add to this image here also another feature, that is the stream tracer. So let's highlight the system.form and then add the stream tracer. As you can see, you can understand already what it will imply. But now let's improve this graph a little bit more. Let's choose a source that is here with the U variable, the vectors, and also the point source. Let's locate it at 1.2 in X and 0.05 in Z, as well as its radius of 0.1. Let's click OK, and also let's change, instead of P, let's color the streamlines with U. Let's click OK, and then let's limit the highest value to 1.5, and that's it. Okay, so you can see here how the streamlines are shaped around the building, how they are accelerated here where the flows turns around the building. So it's quite nice to see how the flow interacts. Again, this is a very simple case, but you can imagine how you can perform this kind of simulation in complex environments and understand the path lines of your flow. So this was the first analysis, but now let's focus on our goals. Let's see how the contours at pedestrian level show the velocity. So let's delete these filters we just applied, and let's start again from scratch. So now let's add again a slice, but this time projected along Z with a normal along Z, and the origin to 0.05. Okay, let's click OK, and color it with U, as well as limiting the peak value of 1.5. So, as you can see, in the first part of the inlet, the velocity is very high, then it is lowered down by the ground, the friction with the ground. So, near the building, as you can see, in the very front part, there is a small bowl where the velocity goes down. In fact, the fluid is deviated on the sides, and as you can see here, it speeds up a little bit. In fact, in these parts here, the fluid is deviated from the building and it is accelerated. And so typically, these are typical situations where the pedestrian comfort has to be analyzed deeply in order to avoid dangerous situation and to improve design. In the back part of the building, there is the recirculation zone with very slow velocity. And so let's now focus on the body pressure. Okay, so let's again delete this filter, and now what we want to do is to see how the pressure is distributed on the building. This is very important in case we want to use CFD to evaluate structural loads to validate our structure. And so let's focus on how to do that. I will highlight in this selecting the system file, then going down, you can, by holding Control, you can select multiple boundaries. Dark orange, that is the ground, white, that is part of the ground, and magenta, that is the building itself. So now I can click on OK, and as you can see here, we have just the ground with the white part and the building. There is already the pressure shown on these boundaries, and I'm going to show you how it is distributed on our building. Let's say, OK. Obviously, OK, it's quite simple, this geometry. Obviously, the highest peak is in the front part, while the lowest one is in the back part. But something important, you can integrate the pressure in these surfaces and to obtain the structural loads. Again, it is a very simple case, this one, but you can apply the very same approach with a complex geometry and you will find the very same result. So that's it for the web application, but let's now go back to the presentation in order to show you a few features that we are going to provide you in the near future. So let's go on the presentation again. Okay, so we just finished our practical application. Let's now focus on the extended features. For urban microclimate simulation, we are going to add very soon the possibility to use a user-defined profile at inlet, and also to simulate pollutant and contaminant dispersion in the area. So let's see how what it means. First, user-defined profile. Typically in the literature, we have a logarithmic low wall wind profile, a power law wind profile. It means that instead of assigning a uniform profile at inlet, you can assign a profile that has these shapes, and that this way it's very accurate and it respects what happens in the reality, so it can give you more accurate results. And that's it. That's what user-defined profile means. They will be available very soon. And then pollutant and contaminant dispersion in your domain field, and basically this can use to simulate, let's say, smoke diffusion as well as pollutant dispersion in a lot of real-life application as well. In case you have to understand if a pollutant is released from a given point source or a given source in your domain, where would it go, and so how to behave in case of danger. Basically, two aspects are very important: the definition of the source of the pollutant as well as the contaminant, that is a boundary, or that can be a boundary or a volume inside the fluid domain, and then visualize results showing the distribution of species inside the domain and how it evolves. And now there is an example here. You can understand maybe better how it works. So this is an example of a real geometry you can use to perform your CFD simulation. What I want to stress is that there is no difference from this geometry and the simple building we used in terms of how the steps are organized and how the simulation works. The workflow is the very same. Yes, you just need to improve the definition of the mesh inside this part of the geometry, but then again, all the settings are the very same, and just, I mean, it may imply more time to perform it, but, and that's the reason why we cannot do that in the webinar, but it's a very same thing. And as you can see here, you have a source of your pollutant that is here where there is the red part, and then its evolution, its dispersion in the field, and how it behaves interacting with buildings around it. So that's it for our presentation. If you want to ask questions, here is how you can do that. You can just click on the small array of squares in the top right of your screen and selecting question and answer. Maybe you need to be logged in Google Plus to do that. And in the meantime, you are trying to asking your question. I'm going to answer a typical question usually participant asks. And they are, for example, do I need any specific hardware for running your web application? The answer is certainly no. You can just run it through a browser, so you can even use a tablet, a simple tablet. It means no hardware requirement at all. In terms of which kind of browser we support or operative system, we are cross-platform as well as cross-browser. Most common one are supported for sure. It's like Internet Explorer, Google Chrome, Mozilla Firefox, and Safari, as well as Windows, Linux, and OS X. Another question usually is if we provide support for new customers, and that's for sure. We provide support at many levels, and for our first customer, it will be something that we are going to do with pleasure, and it can be performed directly online since our web platform, it can be accessed from everywhere just with an internet connection, and we can work side by side. We offer another question is usually about our plans. We offer 4 different plans. There are 2 monthly plans and 2 yearly plans from freelancers to enterprise focused on, and they differ mainly in terms of number of credits that reflects in the number of simulation you can perform. And that's it. Usually someone asks also what happens if the internet connection goes down and my simulation was still running. And that's a good question. Nothing happens since the simulation is on our servers and it will continue till the end. You can just log in back when you have your connection back, and you will find your results ready for you. Sometimes other questions are about how accurate can be the results and how spread is this approach throughout the industry. And CFD is something that has been around since the 90s, and it's a well-proven approach to design, and it's nothing new in that. The innovation we are proposing is to bring this instrument on the cloud and to avoiding you paying a lot of money for things you don't need to, like license or hardware. So that's the innovation, not the CFD. CFD is a well-known and applied instrument in the high technology field, and like, for example, Formula One race car as well as airplanes and these high technology sectors. So if there are no questions, that's it for us, and thank you very much for following Conself, and stay tuned with us because we are gonna show you more webinars in the near future, and let's keep in contact through our websites as well as our socials you can find here on screen. So thank you very much again, have a nice day.